It's my pleasure to introduce Nils Thuerey, who's currently an associate professor at the Technical University of Munich, running a group that focuses on deep learning methods for physical simulation. In particular, they seem to have a lot of expertise in fluids, like I think we'll hear about today. Nils has a long history of working on fluids, including postdoctoral work at ETH Zurich, his faculty position now, and a technical Oscar in 2013 for controllable smoke. With all that, it's such a pleasure to have you. We wish we could have you in person here at MIT, but hopefully we'll be able to do that soon. In the meantime, I'll let you go.
Yeah, thank you very much for the invitation, Justin and Yusuf. And exactly, I hope I get to visit sometime in person, but great it still takes place in this virtual form. And thanks everyone for joining. My name is Nils Thuerey. I want to talk about a topic that keeps my group busy at the moment, and I think that is very exciting, differentiable simulations in the context of deep learning algorithms specifically. So what we are targeting here are physical phenomena. So one good example are the air in the room around us, or the water in a glass on your desk. These phenomena, these materials also come up in a lot of engineering applications. I actually have some animated versions here. Traditionally, fluids are, of course, also very important in aerodynamics. That's the classical application. But from the computer graphics perspective, also liquids and the surface we see are very important. If we think about robotics, there are also a variety of very interesting connections here. One example that combines the two here is shown in this picture. We might have some robots that actually should move through the water, like this robot of a fish here. So all of these involve fluids, and there's actually a large class of other, in a way, very similar physical models and materials that are based on similar descriptions. So all of these play a role in a large variety of applications, and kind of that's what I hope the techniques I'll be talking about will be interesting for in the future. So these are the targets in a way for these algorithms. I have to show the Navier-Stokes equation at least once here. So this is a typical model that we'll be looking at here in a short incompressible variant. This is the established physical model for fluids. So for the talk here now, I want to, in a way, take a very practical approach. So I want to summarize that as follows. We have the physical models. In a way, that's what we want to base all these algorithms on. So they're great, very established, very general, but in a way also very idealized descriptions. Now, to work with them in the computer, we have numerical methods since roughly 1950. So 70 years of development on ways to numerically approximate and find solutions for these physical models. And I think these methods are great. So basically, one of the key goals of my talk will be to keep these. So to use the knowledge of numerical methods that we have. And obviously, as you can guess from the title, we want to combine this with deep learning and specifically. And in a way, you can see the goal there to clean up the mess, kind of the residual towards real-world observations or the numerical errors that are made in these approximations. So that is how I imagine these work together. And this is basically an overview of what I'll be talking about in the following. Yeah, we are, or I'll be focusing on the stop in the middle of these different disciplines. So kind of to show and discuss the landscape of these research fields a bit. When looking at this combination, all of the methods I'll be talking about will be based on simulations. And we can here distinguish whether we actually look at the forward problem, so starting with initial and boundary conditions, and then simulating how they evolve over time, or whether we have a question that basically imposes certain constraints and then tries to find a solution given these constraints and the physical model. Typically, that means we have some kind of iterative process and optimization around the forward simulation. That's typically called an inverse problem. And now this stays, but we want to combine it with the deep learning field. And there are different ways, essentially different ways to couple these two areas. The first one, indicated by this blob here at the top, is what you would call supervised in machine learning. And as indicated here by the position, this is, they're touching basically, but this is not a very tight integration. Essentially, we are using data typically from the physical systems, but it's a relatively loose coupling. And then you can, I think one good way to distinguish different algorithms here is to see it, or to see how closely they couple the two fields. So we can also include the physics in the loss terms. I'll come back to that later on, giving a more tight coupling. But what I want to focus on is actually to really kind of tightly interleave the learning process and the physical simulations. Yeah, so first I want to actually show an example of this non-coupled, of the supervised approach. And here I think weather is a particularly interesting area that we've looked at with a postdoc in my group. So here the goal is really to, in this case, forecast the weather for our whole planet. So it's a pretty complicated and large domain. Here are a few examples already. I don't want to go into too much detail here, but this is a very good example where we use a lot of data. The data is actually assimilated with simulations, but in a way, here the model that was trained really has no idea about the underlying physics. Here's another field that's a bit more complicated, the precipitation. It's much more local, but right, both of these we can basically give to a network and let it produce or we can give some state with the current time to a network and then with the task to predict a future state at 1 or 5 days in the future. As you can see a bit in the middle, for 1 day, it actually works quite well. And then for 5 days, these solutions tend to blur out a bit. But in a way, one of the nice things here was, if you look at the blue line here, this is a kind of full traditional simulation for forecasting. And we can train a network here. If you only look at the red crosses here, that actually reduces the error in some cases or stays on a similar level to a roughly comparable traditional simulation of this weather forecast. So in a way, I think this is an important field and kind of shows that given enough data, this model was trained with a total of 40 years of simulated observations. We can actually do a fairly good job. And in a way, these supervised techniques are definitely have their area and are important in a way. But here, the problem in a way is we don't have any physics in the learning process. And also, it's worth noting this purple line here in the graph, that's the full operational forecasting model. So there's still way to go to actually compete with the output of this model. This just as an example of what you could do if you have enough data. And what I want to focus on next is this integration with physics. And there have been a variety of very interesting papers in recent years on just this topic. So here's just a selection of a few. And I want to focus on the two top ones here from two students from my group, Philip and Kiwon. So these are, if you're interested in details, the works you can find online for additional details. The first one actually targets exactly this topic that I've mentioned before to kind of reduce the numerical errors in simulated environments. And I want to kind of visualize this a bit with this setup here. So if we are considering now solutions to a PDE, then the blue area that you can see here on the left, this is our solution manifold. This is a space of solutions that we're interested in. And now one solution would basically start at a given time, t0 at the top here, and then follow a trajectory in this manifold to a target time. This is the reference. So this is we assume a accurate simulation using higher order schemes or very fine resolutions. So this is the solution, the ground truth that we like to achieve in a way. Now, typically, this is potentially expensive to compute. So we can consider solutions that are, for example, more coarsely resolved or use simpler approximation schemes. This is a bit sketched on the right-hand side here. You can see the rougher polygons in the background. So if we look at the same space of solutions, just downsampled with a downsampling operator here with this tau in the middle, then we could actually preserve the whole space. However, if we would resimulate the same cases, for example, the one shown here for the T0 in this coarser space, we typically have a different discretization and different numerical errors that potentially give us a different solution. So the same simulation in this coarse space might actually look quite different and might follow the orange trajectory here shown. So this is in a way the solution we will still base our learning on and that we'd like to improve. So the goal is here to start with this orange version, with the coarse one, improve it with a learned model such that it gets closer towards this downsampled reference trajectory. So an important thing to keep in mind is we still want to run this coarse solver on the right-hand side and couple it with a learned model. One important thing to note here right away is that we actually have a pretty tough case in terms of shifting input distributions here. So if you think about how some or any inference process here would work, it basically takes data from this right-hand side, from the coarse space. So if we see this in a very simplified, as a very simplified distribution here as a sketch shown on the slide, typically it's very high dimensional, but let's imagine we have essentially a 1D case, then this distribution will actually look substantially different from the one of the reference. We have, on the one hand, the downsampling and the numerical errors that lead to a different dynamical behavior of our system typically. And now we actually want to get away from the source. So we have this green variant in the middle, which potentially has a different distribution that is closer to the reference, but this is something we only have once we do the coupling. So in a way, this augmented method, this improved version, does not exist when we start out. This is not something we can pre-compute, but this basically develops from the interplay of, in this case, a learned model and this coarse simulation. And that is a challenge here, because essentially we later on need a model that works with these changing input features and nonetheless gives us a solution that, for example, pushes us closer to the desired reference trajectories. So this is one of the challenges I'll get back to later on with this algorithm. Yeah, so we can formalize this a bit. In the following, I'll have denote the physics model, for example, Navier-Stokes, the underlying PDE with a P, and then we have these two solution manifolds with phase space points from each of them denoted by R for the reference and S for the source. We have this projection operator, the following called T, and with this notation, if we run a simulation for n steps, you can basically write it in this way. We are typically starting out with one of these reference states from the finely resolved reference simulation, and then this part, it's downsampled, and then basically the sequence of locations of our solver, of the PDE solver, gives us a solution after n steps. And this we want to combine with a learned function in the following called C, that given some trainable parameters theta and a current state S, moves us closer to this reference. So we want to minimize this objective. These projected reference solutions should match the coarsely simulated state plus this correction. That's a central goal in the following. In this setting, if we look at the supervised case, like with the weather again, we can actually use these PDE solvers on the reference and source manifold to produce data, essentially. So we get a lot of these R states and produce a lot of S states. We can store these, essentially build a database, and then train a model with that. So we start with our initial state. We would basically query our model to compute the difference towards one of the reference states. From that, we can compute a loss and then obtain a gradient with which we update the weights in our network. So this is the kind of standard supervised process. This is by now fairly well understood and typically quite stable to train. We need enough data beforehand, but in a way, this is a relatively common procedure. So, as mentioned before, the key is now to get the physics into this picture, the priors, having knowledge about what we'd like to simulate. If we want to incorporate that information in the learning process, then one of the things that actually has been proposed also in a variety of other works is to put that knowledge in the loss function. That would work, for example, like the following sketch here. We again would start with one of these reference states, compute our solution, and then we could basically check, does this solution obtained from the network, does it satisfy conservation laws? Does it correctly reproduce constraints from our PDE formulation? Again, that would give us a loss, and then we can basically compute the adjoint of this residual equation to get back to a gradient on the states, and then again backpropagate this into the network. So it's worth showing this because this is not what we'll be doing later on. This is definitely an interesting method in a way. It, for example, has the advantage that if you formulate the solution with this neural network here, then we can use the neural network to compute these or to formulate the residuals. So this can be leveraged to compute these residual terms. In a way, however, it also does give us a kind of implicit discretization of our solution, and in a way can be difficult to control. And in a way, very, very obviously, this solver component that I had for the pre-computation step, this is not in the picture. So we have something else here, this residual, but we're actually not really using a numerical solver for our PDE. And in a way, this is a goal. We'd like to keep this solver with potentially efficient methods. And this is the goal of the next variant that I want to focus on in the following. So if we have the solver, then one of the key challenges is we actually do need this gradient, this direction from the PDE. So we need the derivative of our PDE with respect to these states, with respect to the input. Well, one of the nice things actually taking it into the learning process is that if we really use the full solver, we can use existing numerical methods. So if we know about what problem we'd like to solve, we can use the existing knowledge to choose a suitable one for fluids, a MACGRID or so, or a fast and efficient solver for inverting linear matrices. It's worth to note that when providing these gradients, it's typically important to think about the granularity. So we typically don't need them for every single operation. In the extreme case, you can actually see it as one step for the whole, say, update per time step of a solver, or maybe important in-betweens. This is somewhat a question of efficiency, but for the learning process, at least, typically we don't need gradients for every intermediate steps, because within the physical solver, we typically don't have any degrees of freedom. There are no weights of a network to update or so. So typically, the most important thing is actually the gradient as it comes out of the physical solver. yeah, one good example in the context of fluid flows is a Poisson problem that's, for example, solved for the pressure correction here. So we have a Laplace matrix, and then right-hand side from the divergence of the flow, we typically need to compute the inverse of that matrix. So we're typically interested in A inverse times B. And then if we derive that with respect to B, what we're left with is actually the matrix, the inverted matrix. And hence, we can, in a way, use the same numerical methods that we used in the forward pass to compute the solve, and the backwards pass, again, to compute the gradient for it. So, right, you can choose your favorite conjugate gradient or multigrid scheme here for both passes of the training. And yeah, we actually do have pretty efficient solvers here, so this could be handled quite efficiently if you choose the right method. And then typically, once we have this for the most important operators, then we can rely on auditive functionality of some deep learning framework to actually combine these in a chain, in a longer computational chain, like the ones I had in these sketches. Yeah, so one thing worth pointing out here in this context now is we want the network to interact with this solver. So in this notation here, actually, we can basically write that we want for n steps, n invocations of both the network and the solver, and they should work together. So this is a bit aiming for these distribution shifts that I mentioned before. So the correction function, the C, which typically is represented by a neural network, now does not just depend on these pre-computed states S, but it actually does depend on states that are modified by the network. So that have gone through the solver and that were changed by the neural network. And now maybe you can imagine a bit these we don't have beforehand, but if we have these gradients, we can actually make sure that our network gets information from the physical operators in our formulation. Yeah, it's slightly less nice if you write it out. So the important bit is basically the correction function now depends on these S tilde states that were modified by previous variations of the neural network. And we typically do this for longer sequences, such that the network actually, and the learning process also sees how the influence evolves over time in a simulation, for example. Yeah, so when showing that in a similar with a similar visualization as the previous one, starting at the same state, but now this neural network and the solver actually work together to produce a new state. So at this right here, at training time for one iteration in our learning process, we're really running the full physical solver as part of the training loop. Typically for a whole mini batch, this might be running multiple simulations at once. That gives us a new state that, again, n times in the end is actually used to evaluate the network and invoke the solver again up to a final state. So this is, in a way, now the whole evaluation process forward with the network. And now for learning, of course, we need to actually get an update for the weights in the network. And this we do by computing the loss. We typically, in this case, have a reference for these future states. So for each of these pieces now, we can basically compute what's missing in the solution. Again, backpropagate through the solver. This is what is provided by such a differentiable physics solver to get to the interface of the network, and here compute the gradient for the weights inside of the network. And this is basically now done, right? So here also the gradient now actually can use the discretization we chose for the solver and for the gradients in the solver. So this actually gives us control over the way gradients are computed in the learning process. And in this setting now, this is done actually for all the n-1 future steps of this trajectory where the network had an influence. Again, going back the chain all the way to the end. And then we would continue with the next iteration, potentially get a new state of the system or several of them, and go through this whole process again. So this definitely involves more computational effort at training time. As you can imagine, we actually have to run the solver here for n steps, and the joint is typically on a similar, has a similar complexity. So this definitely does cost additional computational resources. But I want to now show a few examples that highlight a bit that this can actually help a lot. So we looked at a standard wake flow scenario. We have a rectangular domain with a circle as obstacle, flow from the bottom, and in total training data from 6 different Reynolds numbers. And in this case, these reference manifolds and the source ones look like shown on the right here. At the bottom is the reference. We can see that actually the vortex shedding behind the obstacle is fairly well resolved. And with the coarse discretization, a lot of these dynamics are lost. So that is now, in this case, actually the goal of the network, to basically restore the behavior at the bottom. We can actually also, in this case, compute the mean absolute error. As shown here on the left, is 0.146. In this case, on average, across a set of test data cases with different Reynolds numbers. And this is now directly at the top, the solution of this combined model in the following, denoted by SOL. And you can see visually this now matches the reference at the bottom much closer. And also the absolute error here goes down a lot, roughly by a factor of 10. And these absolute error values now are actually also interesting because they indicate a bit how different these spaces of solutions are effectively. I earlier had this picture with this sketch of a distribution. Again, in this case, it's actually a convolutional neural network that receives a whole kind of stack of data as input. So it's a high dimensional input, but basically this 0.146 MAE that tells us a bit how much of a difference there was and how different also this combined version essentially looks in terms of an absolute error. And if we have the solver in the loop here for training, the network actually at training time really sees these changed inputs. Whereas if we would pre-compute, it would really only get states that are as different as indicated here by the MAE values. Yeah, so we can basically train the model with the actual distribution of input features that it will later on see at inference and test time. So it's worth showing that in motion, these are, after all, flows over time. We've mostly looked at time-dependent problems here. So this is a lower Reynolds number case. You can see the washed out, visually washed out result on the left, and the ones in the one in the middle more closely matching the reference. And on the right side is a higher Reynolds number case with a similar effect. So one interesting point here that I've just briefly mentioned is it's an open question how many of these look-ahead steps we basically should perform at training time. And this graph highlights that a bit for this wake flow case. So now we actually have the relative improvements in terms of MAE over the reference. And this version denoted as NON here, that's essentially the supervised variant with a 29% improvement. And towards the right, you see more and more steps unrolled in this process that I had on the slides before. And that was the N in the previous equations. So here the variant with 4 steps of simulation in every training step actually had 41% error. And on the right side, the extreme case we tried here with 128 steps of simulation basically improved this by another 19% to a 60% improvement in terms of error. So in this case, you can see every bar doubles the number of steps. That doesn't half the error or so, but it yields substantial improvements when letting the network essentially look ahead further in time at during the training. Yeah, and we also, in this case, actually tried a 3D example that's worth showing here. It's a similar case. Again, in this case, a bar in the flow and the inflow coming from the left. And interestingly, in this case, the supervised version did substantially reduce the error, but when using it over time in a longer simulation, these are 250 steps, then it typically cannot keep the simulation stable. So this is most likely caused by exactly this distribution shift. When applying the model, the inputs start to look different, and this accumulates over time. And then the model at some point has problems stabilizing the solution and yields these patchy patterns in the flow. And on the here in this comparison, you can see the version in the middle that combines the solver with the network, and it actually manages to preserve a large part of the dynamics of the reference in the coarse resolution here. Oh yeah, another fun fact to mention here about our paper is there we show it on white background, this 3D case that nicely highlights that in reality the paper is actually about fish smoking cigars, but that's just worth a side note. Another point worth mentioning is that in the end, when comparing these, the performance is of course an important factor because here we are working with always simulated data, so we can compute the reference. It's just in many cases a lot more expensive than this more roughly approximated variant that we use for the hybrid version. And for specifically the 3D example now, the reference simulation for 100 time steps actually took on the order of 900 seconds, while the source solver with evaluating the CNN for every step took 13.3 seconds. So that's a nice speed up of more than 60 in this case. However, of course, this is very difficult to compare. It's a CPU-based solver compared to one that also leverages the GPU for the CNN. So it's definitely to be taken with a grain of salt. But I think what's especially interesting here from such a combination is that all these trained models will potentially see better and better support in terms of hardware in the future. One good example recently was the new iPhone that with the new chip, where the number of cores for evaluating neural networks was doubled. I think the rest of the architecture didn't change too much, but I expect to see very substantial improvements for running CNNs or neural networks in general in hardware. And if we have such a pre-trained model, I'm sure for the next couple of years, we will see very nice improvements in terms of performance just by using the latest hardware. So I think, and potentially full simulations also could potentially be arbitrarily expensive. So I think this gap could be even larger in other settings and in the future. Yeah, another example that I want to show a bit more briefly within this context is controlling PDEs, and this is motivated nicely by the setting here. So with this control now, the problem is slightly different. We still have a physical model, say for air in this room, but now we have a fire somewhere. And the question is, we have some exhaust valves that we can control, where we can steer the flow in and out of the room. And we'd like to move smoke from such a fire as quickly as possible to the next exhaust. Now we're dealing with the flow, the fluid flow in the room, and we have this objective of moving the smoke to a certain location. We're typically picking a fixed point in time. But this is now one of these inverse problems, as mentioned before. And the goal is now to solve this inverse problem with the same methodology as explained so far. So this is now a tougher task because in a way it's much less constrained. We just have a longer term goal with respect to, for example, just observed state, some smoke some marker quantity in the fluid, and there are no constraints for the intermediate part. And because of that, we found that it's actually advantageous to use two networks in this case. One that essentially predicts these intermediate states of the observable quantities of the smoke where it should be. And then we have another network that is more similar to the one before for the corrections that really, in a way, computes an action. In this case, we're typically allowing for forces to be applied to the flow to push around the marker density. Yeah, so in this case, the whole structure looks very similar. We can have a sequence of steps that are computed. Now, in this paper, we actually called this this network CFE network for control force estimator. It interacts with the solver in the same way. It basically applies a force to the velocities in this case. And the main difference is that now we really only have one loss at the very end of this chain at frame n. And then information from that loss needs to backpropagate through the whole sequence in order to update the weights in the CFE network. Right? And the difficulty here is we really have to rely on the backpropagation through all the n steps and -1 steps of simulation. It's typically, especially towards the beginning, the information on how to interact with the flow or the physics are quite crucial after such a long, or potentially long step of simulations. To make it a bit clearer, here's a simpler example. I have a fluid one in a moment, but we can look at a 1D advection diffusion case with Berger's equation. So on the left here, you can see the reference going from the dashed bluish line towards the purple one in the middle here. So this is state we'd like to get. This is a Berger's equation with some unknown force terms. And we can again try this just for comparison, the supervised variant where we basically train a network just for one-time step differences based on pre-computed data. It gets us somewhere, but you can see especially in between these different lines, the solutions are typically very jagged. So it basically has no way of seeing or respecting the evolution of the solution over time. And that is actually what is very strongly improved by this differentiable physics training, which really unrolls the whole sequence at a training time. So the network sees how the states change and then has a chance to actually more smoothly apply forces and also apply less forces here and drive the state towards the target state. In the paper, we have one other variant that improves things a bit more to essentially re-evaluate the control forces as we go over time. Basically, the top predicts in one go before even starting to run the physics, all the forces that should be applied. The lower one basically checks what the current state is and then tries to re-estimate them for the remainder of the sequence. This, I guess, as you can imagine, improves things. And here now we have this setup with the room in a more stylized version. So now the purple region in the middle, that is the room we're interested in. We have three windows at the top, and the blue areas outside are the region where we can apply forces, essentially the exhaust system. And in total, we have still around 5,000 control parameters in the outer region. This is the 128 squared simulation. And we can train the network in the same way for 16 time steps and then give it one of these target regions. And then the network actually learns to essentially solve this inverse problem and give us the forces to drive the smoke into the right direction. So this was trained in the same or a very similar process to the corrections from before. Yeah, so much for the applications. As a small outlook, I showed one 3D example, but I think what will be really interesting is to go towards real-world 3D scenarios. And one area that we are very interested in is flows with visual information. So we have a small multi-camera setup with a fog machine that we can film and reconstruct with some traditional methods, some convex optimization schemes. So we have some reference data there. And I think this will be a very interesting setting to apply similar processes driven by physical priors to reconstruct real-world phenomena. And I hope I was able to illustrate a bit that these differentiable physics simulations are a very interesting tool, and in a way, a very good building block to combine simulations and learning. So as mentioned before, we basically have these two sides, the deep learning methods and the physical methods, models and numerical methods. And I've shown these correction and control examples. I do want to mention the weather again. I've shown this in a purely supervised fashion. And on first sight, it seems like a very bad idea to use here because the simulations for such a weather prediction are extremely complex. They're typically highly sophisticated schemes. However, what I didn't have time to go into too much before is that for the differentiable part, potentially we don't need the full system. So a bit like this reference space from before, potentially we can use a reference from a very complex system and train with a much simpler differentiable solver. And this is, I think, where these similar ideas would be very potentially very interesting also for weather prediction, not to have the full solver in there, but an approximate solver in order to improve the inference of future states. And yeah, to come to a summary of my talk, one basic message is that intuitively, I don't see why there should be any borders between these different sides shown here on the slide. So it really does not make any sense to have cuts, right? Or treat one as a pre-computation step and then the learning as a different process. Ideally, we have information about the actual function we're interested in and all the derivatives. We need potentially higher order ones flowing back and forth between these simulations. There's a nice quote from Thor Heyerdahl that fits into this picture. I think it's good not to think of these two as separate domains or so, but ideally, really, they should go together and work seamlessly together to solve these problems. It's difficult enough, and right, having good numerical methods and good physical priors in terms of models, I think, for the foreseeable future is a very important component to drive and improve learning. And right, ultimately, right, I think they should go together and then also in the end help us to improve the understanding of these physical systems, which is another very interesting challenge, as I'm sure you all know, but also there, I think there's a lot of potential for such learning algorithms. Yeah, and with that, thank you very much again for the invitation and for listening. If you're interested, our differentiable solver is actually available online here. You can see the link. And again, thanks to my collaborators and the funding agencies. Thank you.
Nils, thank you very much for the very interesting talk. So we have time for questions. If you'd like to pose a question, you can put it in the chat or raise your hand and we'll try to look for them. Justin wanted to ask a question.
All right, there's a question. So the reference solver is used to compute all the reference data. That is similar to the supervised process. We typically run the reference solver on a randomized set of initial conditions to produce a training data set, and then at training time, right, you can basically then project this into your source discretization and rerun similar solutions there on the source side.
So Justin was asking, he sent it to me only.
Okay.
Your talk focuses on machine learning for improving physics. Is there hope for the machinery you developed to enhance machine learning?
There are also, yeah, that's a good question. There are also a variety, right, there are several works already that that use physical intuition to improve the architectures or the formulation that we have for machine learning. So I think there's definitely a lot of room there. One good example is this neural ODE paper that sees a kind of iterative invocation of a network as a residual process similar to the popular ResNets. And right, no, I think that's definitely an interesting direction. The terms in the loss function. So the loss function in the end is actually very simple. Typically, we have a discrete state of our physical system, for example, velocities on a grid, it could be a Mach grid or any suitable discretization. In the end, it's just a long list of numbers. And then it's only important to actually have this reference, the reference data, and the same discretization. Then we can compute an L2 loss. And the solver works in this discrete space, right? So once we have a gradient from the loss in this discrete space, we can actually propagate it through the solver. So in a way, the loss is actually a very simple one. In a way, the knowledge is really in the physics solver in these examples. So the next question is whether this approach can work in the level set equation. So if the level set is given on a grid, you can actually very directly run the same process. We've also tried that in some previous works. You can basically discretize your level set update, which is very similar to an advection step, right? And then, for example, use that as a differential operator in an optimization process. So in specifically this setting, I think if you have a discrete version of your level set, that would nicely work. Yeah. And then the next question was data compression on the test data, say with an autoencoder model. That's an interesting point. We haven't done that at all in what I've shown here. Potentially, you could compress these states and work in reduced ones. However, what I've described basically uses a discretization, a discrete simulation on the chosen space. As soon as you encode this with an autoencoder or so, we have some abstract latent space that potentially behaves very differently, where we don't have any good models for how it evolves over time, say. So in the latent space, it's typically more difficult to use physical priors, or I would say impossible, because we don't have very good intuition for, or unless we have a very good intuition for the shape of the latent space. You could, of course, then apply similar ideas on a decoded part after the autoencoder, so to say. I think it's difficult directly with the autoencoder. All right, there was another question. How the model or the trained model generalizes to similar problems. So in this case, so from our experience, actually, the models, the neural networks actually really by themselves don't generalize very well. If you train it on a certain range and we suddenly put in much larger, only larger numbers, a larger range of values or so, then very quickly you run into problems. So also for the cases I've shown, they were specifically trained for this one obstacle and the one shape. Especially for the obstacle shape, in other works, we have actually varied obstacles. I'm quite certain this would also work. It's another data dimension, but I don't see any reason why this would not work. But generalization, I would recommend to typically treat as something where large shifts and offsets are basically normalized. So if you can, the input data, if you can non-dimensionalize it or remove certain offsets, then that helps a lot. Otherwise, I think it's potentially tricky. Yeah, there was another question asked too many times, but no, it's actually it's a good question, how to deal with chaotic behavior like turbulence during optimization. That's a good question. That's definitely tough, right? Our cases had Reynolds numbers on the order of a few thousand, but numerical diffusion that was not fully developed turbulence. And in order to really deal with turbulence, I think you'd also need in this setting, you'd need a solver that actually resolves it at training time. So I think this is definitely challenging and potentially difficult. But I would hope that given enough resources and the right solvers, we could actually really train networks that basically see turbulent behavior at training time and then learn to work with it. But out of the box, I think it would be definitely difficult. Yeah. So the derivatives of the nonlinear terms in the Navier-Stokes equations, this is basically, we really discretize the different operators. So we have the pressure solve is actually not too bad in the sense. That's what I've shown before, what I had on the slides. Essentially, we have to invert this Laplace matrix, which stays the same inverse matrix. The advection term, the transport, is trickier, but we also basically directly compute the derivatives here with a joint method for the steps taken for the forward pass. But potentially, I think, especially for the advection term being so nonlinear, I think there you could also find more accurate and better methods. I think that is potentially one of the crucial aspects of learning, and then also something where a good differentiable operator could yield a lot of improvement. The next question from Wojtek was any comments on grids versus graphs, right? Graph neural networks are definitely also very interesting. I think there are a lot of nice works at the moment improving that and working with it. In a way, I think that essentially gives you a different discretization. So I don't see a reason why it would not work. And also for fluids especially, actually, that would be very attractive. Many industrial applications typically use non-uniform grids, potentially quite complex ones. So having a solver that can handle these and then graph nets that can work on the same structure and do the learning there, I think that would work nicely together. In a way, we demonstrate this on simple rectangular grids for simplicity to use the existing CNN functionality in this typically run in TensorFlow. But I think it should also nicely work with graph nets. And then there was another question about the inputs of the neural network, whether they're invariant. I'm not sure invariant with respect to so basically in this case the inputs to network is typically a window of the simulation. So we normalize them, we do subtract mean and then normalize by the standard deviation of the range in the test data, in all of the data typically. But they are not modified beyond that. It's really typically a region of the CNN normalized in terms of its range.
Great. Thank you very, very much. You timed everything perfectly.
Oh, right.
It's 1 o'clock.
All right, very good.
Yes. So thank you very much for a great presentation.
Thanks again for the invite.
Great.
All right. Then I guess we can close the session. All right. Bye, everyone. Thanks for joining.
Thanks.